In this video, I'll show you how we can find a solution for this first order circuit with the sinusoidal forcing function. So the solution is of two forms or two parts. So I of t will have what we call a particular solution that is particular to this forcing function and a complementary solution. Okay, so let's get started with the particular solution. Okay, so what is the particular solution? The particular solution is just I of t, IP of t, okay? So IP of t, and as it turns out to be that if you review the math, it tells you that with trials, you can assume that this particular solution is of the same format of the forcing function. So it's sinusoidal as well. But the difference now is this sinusoidal has the same angular frequency, but it has a couple of differences. And the first one is having a magnitude other than Vm divided by L and having a phase shift other than, well, we started with 0 in here, we have a phi. If it wasn't 0, it will be something a little bit different. Okay, so what we will do is now we'll assume that this particular solution is this form, and we'll try to find what this A and what this phi is. All right, well, I'll use this trigonometric identity, which tells me that the cosine of alpha and beta plus beta is simply cosine of alpha times cosine of beta minus sine of alpha sine of beta. Okay, so let's get back in here and just substitute instead of alpha and beta, we're going to be using just omega t and phi. All right, so what we'll end up with is A of cosine omega t cosine of phi minus A sine of omega t sine of phi. All right, so I will arrange the terms a little bit. So what we will end up with is the particular solution is A cosine of phi cosine omega t minus A sine of phi or phi times sine omega t. And now what I can tell you is these are not functions of time, so I can rename them because they're constants. So I can rename this A1 and this one is A2. The A2 includes the negative. So if I rewrite IP of t, which is a particular solution, it tells me that A1 cosine of omega t plus A2 sine of omega t. Okay, so this is what we need. At this point now, we need to find what A1 and A2, okay? And the way we can do it is, well, if it's a solution to the original equation, the one that we have in here, we can substitute. Specifically, we can say, well, I will substitute in the original equation, and the original equation is this one in here. Okay, so if I'm actually to copy it in here just so that we have it next to us. Okay, so we can copy it, we'll paste it in here just to see it. So what we can do is we can say, hey, let's substitute this equation in there. Okay, but this original differential equations also have the derivative of I, not only the I, so we need to find the derivative. So what we can say is we can say the derivative of the particular solution times d of t is simply negative A1 omega sine omega t plus A2 omega cosine omega t. Now we'll take these two, we'll substitute them in here, and what we end up with is the derivative negative A1 omega sine omega t plus A2 omega cosine omega t, all right, plus 1 divided by L divided by R, and this whole thing is multiplied by A1 cosine omega t plus A2 sine omega t equals V of m divided by L cosine of omega t. All right, so I'll rearrange the terms so that we will have the omegas, the cosines together and the sines together. So let's arrange these cosines in here with that L divided by R. Okay, so what we end up with is the following, which is 1 divided by L divided by R, A1, and plus A2 omega, and that here, the whole thing is cosine omega t, plus, and now let's take a look at the sine. So the sine would be this sine, and the sine, of course, we should not forget to multiply here, this sine. All right, so what we end up with is for the A1, it will be negative A1 omega plus 1 divided by L divided by R A2, and the whole thing here is sine omega t, and that here is equal to Vm divided by L cosine omega t. Well, now what we can say is these are two parts of the equation. So this cosine is similar to this cosine. So that means this particular coefficient should be equivalent to this particular coefficient. So let's write this. So what this tells me is 1 divided by L divided by R A1 plus A2 omega should be equal exactly to Vm divided by L. Similarly, we can say that this here sign, on the other side there's no sign, so this here should be equal to 0. So what we can say is negative A1 omega plus 1 divided by L divided by R A2 should be equal to 0. So these are two equations with two unknowns, and our goal is to find what A1, A2, A1, and A2 are. With a little bit of cleaning, and a solution, we'll end up with the following. We'll end up that A1 should be equal to R times Vm divided by R squared plus L squared omega squared, and A2 should be equal to L omega V of M divided by R squared plus L squared omega squared. Okay, so we found what A1 and A2 is for this particular equation in here. All we have to do is just substitute it to figure out what IP of t is. So let me just copy this so that we can have it. All right, so we'll take this one here, we'll put it right here, and we can say, well, let's take this A1 and A2, we'll substitute the A1 in its place and the A2 in the place that it's supposed to have, or it's supposed to go, and we can say that the particular solution should be the following. R times V of M divided by R squared plus L squared omega squared, and that's multiplied by the cosine of omega t, plus A of 2, which is L omega Vm R squared plus L squared omega squared, and that is sine of omega t. All right, so this is the particular solution, and it has a cosine and sine, and well, our goal was not to find something in terms of cosine and sine, but we just did that so we can find these A1 and A2. But really, where we started with is this part in here. My goal is to come back to the original, which is just A and a cosine. Okay, so we found this particular solution now. We've substituted what A1 and A2 is, but A1 and A2 originally were A and cosine phi, so that should help me figure out what these A and cosine of phi. So let me just copy this and tell you, well, this is what we originally have. Okay, so we're going to copy this and just to show you. So this is what we have. Okay, so now we can say, well, this particular one in here should be equal to A1. Okay, so let me just do this here and tell you that this is basically A1. Okay, and on this part, which is A2 including the negative, what we have is we have the following. So these one in here should be equal to whatever that is here. So all we have to do is just equate them. So we have A of cosine of phi or phi, it should be equal to R times of V of M divided by R squared plus L squared omega squared. And similarly, we can say that negative A sine of phi, or we can just move the negative to the other side. Well, I'll do it later. So for now, it's L omega V of M divided by R squared plus L squared omega squared. So what I said by moving it to the other side, so we'll remove the negative from here, we'll put it from here. All right, so we can do a few things. Again, our goal at the end of the day is just to find out what A is and what phi or phi is. Well, we can start off by saying if I divide these two by each other, I will get the tangent. Specifically, the tangent of theta or phi is simply a cosine divided by sine. Or actually the sine divided by the cosine. So it's sine of phi divided by the cosine of phi. Of course, if we multiply by A, nothing changes, but this tells me that I can use these equations, just divide them by each other, divide the sine divided by the cosine, and I should get both. And that tells me that means I will get the tangent to be, the sine is L, well, there should be a negative L omega of V of M divided by R times V of M. Of course, I divided this by this so they go away, they just cancel each other. And this V of M here goes with this V of M. So what I'll end up with is the following. Phi should be the tangent, okay, or the inverse tangent of negative L omega divided by R. But actually, I can put the negative in here outside the tangent. And here is my phi, which is part of the solution for the particular solution that I was looking for, the original one. Okay, the one in here. Let me just scroll. So remember, it's like what we're trying to do is we're trying to find what phi is, and we're trying to find what A. We just found this one here, so that leaves us with a A. So going back in here, how can we find A from these two? Well, what we can do is you can tell me if I take the square of both sides and I just sum them up, okay, or both of them, sine square of A, what I'll end up with is A squared plus cosine square of phi plus sine square of phi, which hopefully you can tell me it's A squared. So what I'm telling you is if you take the square of this and the square of this and sum them, you should end up with A squared. Okay, so let's do that. So A squared equals R squared Vm squared divided by R squared L squared omega squared, the whole thing squared, plus it will be L squared. Well, there's a negative, but with the square it will go, the negative goes away, squared Vm squared R squared plus L squared omega squared. Okay, the whole thing squared. All right, so now we do the algebra. What we'll end up with is the following. I believe we'll end up with Vm squared. That will be R squared plus L squared omega squared divided by R squared plus L squared omega squared. And that's here square, and this is also square. However, what we can say is this will go with a square in here. So what we'll end up with is the following. A should be equal to V of m divided by the square root of R squared plus L squared omega squared. All right, so this now here is the second thing that we're looking for. So now we take it and substitute it in the original particular solution equation. Let me just copy it here just to show you. So we did say that the particular solution should be this one. Now I have the value for A and the phi. Okay, the one that are highlighted. So here's how the particular solution looked like. Okay, so all I have to do is just substitute. So I get IP of t is simply V of m divided by the square root of R squared plus L squared omega squared. And that here should be multiplied by the cosine of omega t. And the phi is negative tangent of the inverse tangent actually, L omega divided by R. Okay, just write this one here R, and this one here is omega. All right, and we get this way, we just get the particular solution for the original differential equation. So this is the particular solution in here. And by the way, this particular solution is the steady state solution because it is a function of t and it does not disappear after some time. It just stays. It tells me that the particular solution, the current is actually sinusoidal, the same frequency omega t, and has this particular phase shift and this magnitude. So what we did find is the half of the solution. So remember, this is the original differential equation that we're trying to solve, and we said it's two parts, it's a particular solution and a complementary solution. So we found that particular solution, the one that I just highlighted. So next, what we need to do is we need to find what the complementary solution is, and that is simple. So we take the original differential equation and we can say, okay, so what is the complementary solution? So the complementary solution tells me, well, you take the original equation, the original differential equation, and you remove the forcing function completely. And what you do is you set it up to 0. And this is what we call the homogeneous solution. And now this is IC of t and this is IC of t, and you continue from there. And now we just find the solution, and the solution is straightforward. So the solution, which is we call the complementary solution, is of the shape a e to the negative t divided by L divided by R. Well, this one here should be a constant, but we should know that it's tau, which is the time constant. And this a has nothing to do with the a for the particular solution. I just called it a for now. Okay, so all right, so we know that this is the solution. Well, all we have to do right now is figure out what this a is. But the way we do it is using initial conditions. So what we need to do is we need to say, well, I of t is two things. It's actually the complementary solution, which is a e to the negative t divided by L divided by R. This is basically the total solution. And the solution we just found, which is here for the particular solution, which is Vm divided by the square root of R squared plus L squared plus times omega squared cosine omega t minus the tangent of -1 omega L divided by R. So we'll have to use this equation to find what the value of this constant A is. And if you remember, the circuit is just simply a voltage source with a switch in here, and then there's a resistor, and then there's an inductor. Okay, that's R and that's L, and at t equals 0 will be 0. So if we assume that initially there was no current flowing through these inductor and resistor combination, we can say, well, at t equals 0, what we have is IT happened, or I of 0, it happened to be 0, and what we have to do is just substitute in this equation. So what we have is 0 equals A e to the power 0, which is just simply 1, plus, and we have to put V of m, the square root of R squared plus L squared omega squared cosine. This is 0 minus tangent minus 1 omega L divided by R. But of course, the cosine of negative theta is the same as the cosine of theta, so we can just technically take these out. Okay, that's what we're left with. So now what we can do is we can say just A is just simply negative V of m divided by the square root of R squared plus L squared omega squared cosine the tangent to the power negative 1 omega L R. And now what we have to do is just take this A here, substitute it by its value to get the complete solution for I of t is negative V of m divided by R squared plus L squared omega squared. And that here we multiply by the cosine of tangent to the negative 1 omega L divided by R, e to the power negative t divided by L divided by R, plus V of m. So this part here that we wrote is what we call the complementary solution. It's the solution for the homogeneous equation where there's no forcing function, and t appears to the power of e, which dissipates, which tells me this is the transient response, divided by R squared plus L squared omega squared, and that's here cosine omega t, so t appears in the cosine in here, negative 1 omega L divided by R. And again, so this is here is the final solution, and it is two parts. So the first part is here, which I'm referring to it as a transient response, and the second one here, which is the solution for the particular input where the cosine or the forcing function is a cosine. So this one here is transient, okay, and this one here is what we call steady state response. So the first part is transient because t appears to the power of e next to a negative in here. So this here, after a little bit of time, which is 5 taus, 5L divided by R, will just disappear, while t appears in the cosine, which tells me that there's a sinusoid that will stay as long as the switch is closed. And that here is the solution for a first order differential equation with a sinusoidal forcing function.